We shall never be able to directly measure details of quark motion. Just confirming quark's existence requires high-energy collisions, which put an end to this motion and destroy the structure of the proton or the neutron. And yet, we know a great deal about this motion. It's very fast. Even the slowest quarks in large atoms move at 80% of the speed of light. A more normal speed for a quark is 99.995% of the speed of light. The motion is restricted to a very tiny space, that of a proton or a neutron, which is vastly smaller than the atomic orbital in which an electron moves. The motion causes chromodynamic bonding, which give protons and neutrons the property of mass. The mass property is simply a gravitational attraction to other mass in our galaxy. There are 2 up quarks and 1 down quark in a proton, and there are 2 down quarks and an up quark in a neutron. While quarks move, they emit an electromagnetic field, which moves out at the speed of light in all directions. In the direction the quark is headed, the field is intensified because the quark keeps adding to the field to the very same space. If we take some same sign quarks like up quarks and send them at high velocity one behind the other, the leading charge will curve due to the magnetic force as it seeks to evade this intensified field coming in the forward direction. So it curves to get out of that intensified field. When you have 2 like sign quarks heading together in the same direction, with the first one being forced to curve, they will separate electrically. So their gap between them will grow. To prevent this, we need to introduce an opposite sign quark between them. If we further specify that the spacing shall be a gap of 6 to 1, the gap between the first up quark and the down quark is 6, and the gap between the down quark and the trailing up quark is 1. If we make that further specification, we'll find that it's possible for all 3 to be curving and the forces between them to be all pushing forward, balancing against the speed of light. So how does this work? Well, if we look at the down quark, it will seek an intensified field. It will seek an intensified field. So the field coming back from the leading up quark will be intensified to the outside. So it will seek to go that. But the field coming to it from the following down up quark is intensified to the center. Now you would say, well, 6 to 1, so the field from the trailing one will be the stronger field. But that is not correct, because in the direction of motion, the field only has to travel half the distance before it is met by a following quark, whereas the trailing quark's field must travel quite a distance before it can catch. It's going to be the difference in their speed which results in it being able to catch, and it won't catch it until a greater distance has been traveled. So that's why the second quark is also, the down quark is also trying to curve. Now if we look at the trailing quark, it gets the field directly back from both, so again we can just measure distance. So the overriding force will come from not the leading quark but the down quark. So the down quark's field is what has the bigger effect on the trailing up quark. And of course the field from the down quark is intensified to the outside because it's the field that's coming back, so it's more intense on the outside, and that is what the opposite sign will seek. So the magnetic force on the trailing quark will also be to curve. So now we have the three quarks with net forces to curve. And so this is a possible condition for a circling a circling effect, which is balanced, a balanced circling effect. We should keep in mind that magnetic forces can be extremely powerful when you have such high-speed quarks. The reason for this is that the amount that the field is intensified forward is a function of the speed of the quark that is making the field, and the amount of field and how this intensified forward field is felt is a function of how fast the other quark is moving through the field. How much of the field does it reach? So now we have velocity squared, and when you get two things moving as fast as quarks do, this is why the forces can be so strong in upper chromodynamic bonding. The condition for quarks to circle in the same plane are, one, that the forces pull into alignment. If the forces are all pulling into an alignment, that will hold them in the same plane. And two, if the electrical forces do not cause changes in spacing. To look at this, we'll need to map out the intensity wake that a circling quark would produce. This is actually a fairly simple thing to do, because the fields move at the speed of light and the quark is moving at almost the speed of light. So we can, if we draw a circle that the quark moves in, and we divide it up into, say, I found 15-degree intervals was good for graphing purposes. And then you ask yourself, well, you put your quark at 12 o'clock, and you say, where is and then you go back one interval and say, where's the field? What happened to this field one interval back? Where is it now when the quark's at 12 o'clock? And you find it's just slightly ahead of the quark. If the quark was a pinpoint, the field should be just ahead of the quark, because the quark has gone in a curved path and the field has gone straight. So it's just a little ahead. And you go to the next interval and you say, well, where's this field now? And it will have gone a little further than the last field, just a little further, because again it's gone straight 2 intervals and the other one went straight 1 interval plus a slight curvature. And if you keep mapping them in this way, after you've done about 8 intervals, you'll find you're fully outside the circle. So anything that happens at 8 intervals back, beyond 8 intervals back, has already passed completely beyond the circle. So now we have a full description of a diagram which shows us exactly what's happened to the field, everything inside the field, where the quark was when each field was generated, which touch every point. And you'll see, I'll have a drawing of it, which I'll try to get to show up on. We can now see the direction the field has traveled to reach any point on our circle, and hence we can plot the direction of electrical forces reaching quarks in any location on the circle relative to a quark at 12 o'clock. We can use Coulomb's law to compare the electrical forces on each quark, because we have the charges, the distance traveled from the field origin, and we also have a fairly simple factor for relativistic compression of the field at all angles. Now, if you'll recall this factor for the field compression, the relativistic compression of the field, the angle was relative to it's the tangent of the field origin, and so wherever the field left, the direction the quark was traveling when it left, and then the angle it makes with whichever location we're looking at, that's our angle. And the expression was c minus v times the cos of that angle. Now if v is very close to c, it's even simpler. It becomes simpler. So it's very simple to calculate the relative values of those forces. Note we're assuming there's no motion between the quarks in the stable position that we're looking for, and so all we need to do is to compensate for the Coulomb's law works, because everything is stationary in the final position. Relative to each other, it's stationary. The only thing is that the field is compressed due to the motion relative to the fabric of space. So which I'll talk more about what the fabric of space is in other videos. Note that magnetic forces can have no impact whatsoever on the spacing of three circling quarks, because magnetic forces are perpendicular to velocity. So there'll be no impact whatsoever. These huge magnetic forces cannot affect the spacing. So for the spacing, we have to look at the much weaker electrical forces. And I found that the 6-to-1 gap produced electrical forces which netted out to be forward on all three quarks. Forward balanced against a resistance to moving at the speed of light. So that was what balanced them. And remember that when you're circling, fields that move out less than 90 degrees, reach the quark from behind, and so if they were pulling, they would be a pull back against the speed of not towards the speed of light. However, for fields which reach the quarks at more than 90 degrees, those ones will reach the quarks moving forward, and so attraction of those ones would be a pull forward as opposed to a pull back. That's just a thought that when you're doing your when you're mapping out your electrical forces, you have to also, well, remember that the geometry is very crucial. So the last thought is, are the circling quarks self-aligning? Looking at our proton, we see that the leading up quark curves to escape the stronger repulsive centrally intensified field coming from the trailing up quark. So it curves to escape that. And that's not it'll curve in any direction to get away from that central pull, so it's not aligning. However, the force to straighten up, the weaker force to straighten up caused by the down quark, is a central intensified field, and it's going towards that central field. So it's a single point, so it is aligning. That's aligning. So that keeps it in alignment. The force to curve doesn't have alignment, but the straightening up force gives it alignment. If you look at the down quark, the force it gets back from the leading quark, which comes more directly, so that it is the stronger force, coming straight back and meeting it halfway. at a distance of 3. That's the stronger force. And that one is a opposite signs. The intensified field is to the outside. And it's a cone, so it could be anywhere to the outside. So that stronger force is anywhere on the outside. And then the weaker force, the all from behind, it is also a pull. I mean attraction. Again, it's the attraction. It's attraction, but now it's from behind and it's essentially intensified. The weaker force is centrally intensified again. So again, it's got that same alignment from the weaker force. The stronger force is not aligning, but the weaker one is. So again, it has alignment. And lastly, the forces on the trailing up quark. The trailing up quark. It's comes out to be, well, the stronger force now. Both forces are coming back, is from the opposite sign down quark, which is just in front of it, one space ahead. So it feels strongly that the attraction force to curve is the stronger force, and the force coming back from the leading away from the towards the center reduced field. It's again directed to a center, and it's aligning. So yes, the answer is 3 circling quarks are self-aligning. They would align. So it would simply be a question of adjusting the radiuses ever so slightly of the circle they're making, with the speed of light balancing the forces in such a way that you can achieve pretty much any, by slight adjustments in the radius, you can get large force corrections, so that they can curve to a similar level. They can curve equally. Because I wasn't sure exactly how the speed of light, force, the resistance to force occurs, I was unable to finalize the total gap between the 3 quarks, except I found that it had to be well below 65.4 degrees. It has to be below that in order for the correct signs of forces to occur. But how much below that? I came up with, I've been working with 35 degrees for my total of 7 gaps, but it may be slightly different, of course. The true value will be slightly different than that. Well, my next video will look at how circling quarks produce fields. Well, they produce the fabric of space,